So, we're talking about burning velocity, kinematics of burning velocity. I showed you a simple experiment that one could do to measure the propagation speed of a flame, but of course we want to define this a little more rigorously. In a sense, the burning velocity, we define it, we call it the unstretched laminar burning velocity. We define it as the speed that a flame has, a flame that is infinitely large and not curved, an infinitely large flat flame that burns into an unburned fuel air mixture. Okay? So that speed, that's the speed of that flame relative to the unburned mixture, that's what we call the laminar, typically what we call the laminar burning velocity. And so that depends on different things. It depends on the fuel you have. It depends on the fuel-air mixture, the equivalence ratio. And it depends on the pressure. And it depends on the temperature. Okay? So basically, it depends on the fuel and the thermodynamic state you have. And of course, if you have the fuel-air mixture is diluted, with an inert gas, then, that also changes the burning velocity and so on. So a more controlled experiment that is used to determine the laminar burning velocity. Of course, you cannot create an infinitely large flame. More controlled experiment that people use is a spherical combustion vessel. Maybe for those of you who use a device like this, many people call this, I don't know, the chemists started doing this, I don't know. But many people call this a combustion bomb. Bombs are supposed to disintegrate. A vessel like this is not supposed to disintegrate. So don't call it a bomb. Call it a vessel. What's that?
Constant volume chamber.
Constant volume chamber. Call it whatever you want, but not bomb. Okay. So people get annoyed with me when I correct them all the time. People say, "Oh, this combustion bomb." I say, "No, it's a vessel." And then 2 minutes later, well, the combustion bomb. No, it's a vessel. So maybe at some point it will stick. As I said, I don't care very much about terminology. Use whatever you want. But if something is obviously wrong, also in a time where the word bomb, might cause you more trouble than it does good. Okay, this is a constant volume spherical combustion vessel. We fill this with a fuel-air mixture, and it has an electrode which provides a spark in the center of this, and so it ignites the mixture, and you have a spherical flame that propagates through this vessel and burns the mixture. And so you have optical access here from maybe you have illumination from one side and you have a camera on the other side, so you can track the size of this spherical flame as a function of time, and then from this you can get the change of the radius with time, okay, dRdt. That's basically what you measure, and it turns out that the dRdt you see, that is the unburned, the velocity of the gas on the unburned side, which you see the outer side, plus the burning velocity with respect to the unburned gases. Okay, so that's the RDT. And so if you measure this and you can estimate or you can determine this VU, then from this you can determine the unburned the burning velocity. This is the device that we run in our lab. This goes to relatively high pressures. It's actually not really pressure limited, and it's spherical. And you see here, this is the window. This is the electrode. And you see in the beginning a spark, and then you see the flame is really very spherical. It's disturbed a little bit here by the electrode, but it's mostly spherical. You see that, so this is the setup. There's a laser. This is an old setup. We don't use this laser anymore. We use diodes now to illuminate this. There's actually, the art is in providing just enough light that is not overexposed, that you still see the structure. Because if the flame develops instabilities, it's not flat anymore, then you would measure some speed, but not the laminar burning velocity. So it's important to kind of see the structure. You see here the flame is all flat in all dimensions. We track the dRdt, which you can easily geometrically see from this. We track this only for the first part, because if this burns, the pressure will increase in the vessel. And we track it only up to the point where the pressure has not increased significantly enough to change the burning velocity. Okay? After that, the pressure is too high, then you would measure the burning velocity at a different pressure. Okay, so that's the experiment. Then the question is how to evaluate this. So you see that, so if we first look at these velocities, what's the velocity in the unburned and the velocity in the burned? If the velocity in the burned, you see you have the flame here going to the right, and on the other side you have the flame going to the left. So in the burned here, the velocity actually must be 0 because of symmetry conditions, okay? Because it's symmetric, you can't have the flow towards the center from all directions, and you can also not have the flow away from the central point in all directions. So in the burned, the velocity has to be 0 because of symmetry, which means that the expansion that you get, you have to see it in the unburned velocity. So the unburned velocity actually is not 0. So if you look at the mass flux then through the flame, or the relative velocity, then the relative velocity on the unburned side is Vu minus dRdt, and on the burned side, the relative velocity is Vb minus dRdt, okay? And if we set Vb, so that's the velocity relative to the flame front, or let's say it's the velocity that goes into the flame front and comes out on the other side. And if we say Vb is 0 because of symmetry, then the mass flux through the flame is here, the unburned velocity times the relative velocity, and then it must be equal on the burned side, burnt density times the relative velocity, and again the Vb here is 0, so you get this. So this gives us this relation here, gives us this relation, but this is also equal to Vu plus SLU, we said earlier. So here from the right-hand side you can get an expression for Vu, and so this is this, and this I can plug in here again, and then you see I get an expression between dRdt and SLU. This is exactly what I want, because I measure dRdt and I want to know SLU. This is all simple algebra, and it comes out to be this. SLU is dRdt times the density ratio. The density ratio then we determine, just from burnt gas conditions. We assume the burnt gas is at equilibrium, and then we can compute the Rb. This is just the unburned density. So if we know this, we can compute the SL. Now, the burning velocity as such is defined with respect to the unburned mixture, meaning what is the propagation speed of the flame relative to the unburned gas, okay? I can also define the propagation speed of the flame with respect to the burnt gas, which is different because the velocities in the burned and the unburned gas are different, and so it's different here by a factor density ratio. So we call the one SLB, the burning velocity with respect to the burnt gases, and SLU is the burning velocity with respect to the unburned gases. And typically, when we talk about burning velocity, or we call it SL without the U, we always mean the burning velocity with respect to the unburned gases. Okay, that's just the typical convention. Another fact that's interesting is that we said earlier that burning velocity somehow depends on the curvature. So really what you can do is, at any point in time here, you can evaluate dRdt. and dr dt gives you then the burning velocity. And while the flame grows, the curvature goes down, okay? So you get a burning velocity as function of the curvature. And what you do then, you extrapolate that to zero curvature, and that would give you the unstretched laminar burning velocity, okay? So that extrapolation step is not shown here, but I'll show you later how this looks like. Let's see. So one can compute the laminar burning velocity with codes like Chemkin, Cantera, I guess also does that, and here our Flame Master code also does that. And the equation, I want to show you the equations real quick. So this here is a burner stabilized flame. Some of you might have heard the term McKenna burner. So you have a flat burner. Out of the burner, you typically a porous kind of a surface. Out of the burner, you have a flow of premixed fuel and air, and that then burns. And you see here a flat flame. So you see on the bottom here, you see the burner, and above this, you see the flat flame. And what happens now is that the velocity that you have, the fuel air velocity, that in order to match the laminar burning velocity, that should be exactly equal to the laminar burning velocity, right? So if it is, let's say the incoming flow has exactly the velocity of the laminar burning velocity, then the flame doesn't move, okay? It just sits there, it burns with a certain speed, and the flow comes with the same speed, and so it just sits there. Now, if I move this flame a little downstream, and then again I have same velocity, then it should stay there, okay? So the position of the flame is invariant. You know, I can put it anywhere, and really, in fact, it's not stable. It's impossible to stabilize a flame like this. So if the velocity now, the incoming velocity, is slightly higher than the laminar burning velocity, what will happen? It will blow off, okay? If it's slightly lower than the laminar burning velocity, then the flame will burn towards the burner, and then it will attach to the burner, meaning you have heat losses to the burner. Because of heat losses, the laminar burning velocity goes down, and it will stabilize exactly in a position where the heat losses to the burner make the burning velocity exactly the velocity of the incoming stream, okay? That's then the stable point. That's also a stable mechanism, because if I push the flame now artificially a little closer to the burner, it will have more heat losses, it will be slower, it will move back. And if I push it a little downstream, then you have less heat losses, it will be faster, and it moves back to its position, okay? So that's a stable mechanism. But that mechanism, but that flame now, it cannot be used really for measuring the burning velocity. There is a technique, it's called, what's it called? The so-called heat flux burner, which actually tries to control the heat flux of the burner such that it's adiabatic, and then the flame would stabilize without a gradient into the burner. And that's also used to measure burning velocity. But here, so if you compute the burning velocity, then you would compute a flat flame like this, and but in a way that the flame, in computation you can do these things, that the flame sits very far away from this burner, and it should just sit in a certain position. Again, it's translationally invariant where exactly it sits, but you have unburnt gas on one side, you have burnt gas on the other side, and you know, the flame will just stand there and burn. And so you see that if this flame is infinitely large in these directions, then it's a one-dimensional problem through this flame, And that's also how we write this, the equations. So if I write the continuity equation for a steady state one-dimensional system, then it's just this, d rho u by dx is equal to 0, okay? The mass flux has to be the same everywhere, that's what it says. And then species equations in 1D look like this. Energy equation in 1D look like this, and here we use the Low-Mach approximation, and that's about it. Okay, so in the temperature equation here you have a convection term, you have the heat conduction term, and then this chemical source term, which leads to the temperature increasing by chemistry, and then this is the pressure work term for constant pressure combustion. Here this case is constant pressure, this term is 0. And then this here is actually the flux of energy by species diffusion, okay? So if I have a species with a high energy, chemical energy diffusing left, and I have a species with low chemical energy diffusing right, that gives me a difference in energy, which you see in the enthalpy equation. Here, actually, you just see these fluxes, which might come from the fact, different fluxes, which might come from the fact that the Lewis numbers are not equal to 1. Okay, so these are these terms, and similarly, here you have the species equations. Now, what's interesting is you can integrate the continuity equation. So the integrate continuity equation just says rho u is equal to constant, okay? And then you can say rho u is equal to rho unburned times SL, okay? So rho unburned times SL, both of these are constants, and so I can replace the rho u here by rho unburned times SL. So this is all, these are all constant, okay? That's what the continuity equation gives us. And then what's interesting is that now, so this here is a diffusion term, this is a heat conduction term. So both of these are elliptic equations. So they need boundary conditions on both sides, okay? Boundary conditions on both sides means that, you know, you have boundary conditions here in the unburned gas. Is basically the boundary conditions are on the unburned side, you have a certain composition. Okay, that gives you mass and a temperature. You know, that's what you adjust in your burner if you do an experiment. But also here for this case, the gradients need to be 0. Okay, on the unburned side, and on the burned side also, the gradients need to be 0. Which means now I have 3 boundary conditions. Okay, I have gradients in the burned, gradients in the unburned, and the composition and the temperature. Okay, so it's too many, which means always when I have more boundary conditions than I can satisfy with the equations, I get what's called an eigenvalue problem. So this is an eigenvalue problem where a solution that satisfies all 3 boundary conditions exists only for one value of this parameter SL. Okay? So you can imagine if I want to solve the equations, I solve the equation for a given value of SL, satisfying 2 of the 3 boundary conditions, and I check the third and it's not satisfied, then I vary SL up to the point where all 3 conditions are satisfied. Okay? So there's only one value of SL that satisfies the equation and the boundary conditions, so the SL, that's an eigenvalue. So numerically, is not too complicated, but one has to know how to solve this, and then one can solve this numerically, and so this is always a trick that's being used there. Numerically, these equations can be solved if we have a chemical mechanism. This here shows a laminar burning velocity for methane air flame. This is a really old and short chemical mechanism. So this is not very accurate. These are experiments here. You see the black ones here by Professor Law. So go tell him during lunch you saw his excellent experiments in my class. And these are other experiments here which have been compiled here some time ago. So what's interesting here is that this is methane. And methane is what we call a C1 fuel. It has one carbon. Okay? So I'll show you later how oxidation of methane proceeds. But you actually don't need C2 species. Acetylene, ethylene, ethane, you don't need these in the mechanism, really, you would think. But if you neglect these, you see then the burning velocities here are too slow. This considers the C2 mechanism, and then the burning velocities are better, especially at rich conditions. What happens is that at rich conditions, methane goes to methyl radical, and two methyl radicals combine to the C2 chain, okay? Now that's interesting because if you have methane, which then directly, let's say, goes to CO and CO2, that seems to be slower than first going to C2 and then back down to CO. And so you go, the direct path, it's slow, and you go, a longer path, a more complicated path, and it's much faster. It's not much faster. It's faster. Okay. So I'll show you later on also why that is. But anyways, you can compute these, and what you see here is that if you go to very lean conditions here, then the burning velocities get very slow, and we go to very rich conditions also, you get very slow. And also you see there's strong sensitivity here. So if I change the equivalence ratio by just a little bit here, maybe I change the burning velocity by a factor of 2. So that's when instabilities, these thermoacoustic instabilities occur. And then the other thing you see here is that at some point there are no burning velocities here anymore. At some point this flame will just extinguish. It will not burn anymore. This shows you pressure effects. So this is the burning velocity for different pressures as function of pressure. And you see this is logarithmic, this linear, which means this is approximately a power law. Okay? So the pressure dependence is approximately a power law. This is the temperature dependence. These are lines for different temperatures. And you see, of course, higher temperatures in the unburned give you higher burning velocity. And that is roughly exponential, and it's obvious why that is. Higher pressures give you lower burning velocity, as you see here. So what's interesting is that in an engine, you have compression, or let's say, first of all, the laminar burning velocity for methane air mixture at atmospheric conditions, atmospheric temperature and pressure, is roughly 40 centimeters per second. Okay, that's a good number to remember. You want to know that things burn at roughly half a meter per second. Okay, is not 1,000, is not 0.01 meter per second. 40 centimeter per second is a good thing to remember. Okay, other hydrocarbons are in the same range. Some can be twice as fast. Some are slower. But that's a typical number here. In an engine, then you have compression, which increases the temperature, which would give you a higher burning velocity, and it increases the pressure also, which would give you lower burning velocity. So in an engine, this is the line of isentropic compression. You see that. The burning velocity gets a little faster at top dead center in an internal combustion engine, but it's not much faster, okay? So you see here we go up to 700 Kelvin, maybe 20 bar, but the burning velocity here is maybe close to twice as fast, but not much faster, okay? So that might be an interesting fact. Okay, so the burning velocity is a fundamental property. It's a property of the fuel, and of course the state. The burning velocity is often used to validate chemical mechanisms. But it's also very interesting. Recently, at least in Germany, burning velocity became very interesting because if you have a fuel that has a high burning velocity, it can increase efficiency of engines. Okay, so that's a very important effect. And now, if we talk about new fuels, synthetic fuels, e-fuels, biofuels, I mentioned this last time, we could actually design the fuel to have large burning velocity, which would then give you higher efficiency in an engine. Okay, so burning velocity is a quantity that is very interesting, at least to that industry. It's also very interesting, you know, for gas turbines, as I mentioned, where instabilities happen as a result. It's also very interesting. It's also, I mentioned this yesterday, for safety aspects. I mentioned we do measurements for burning velocity for these refrigerants to understand if they are dangerous or not. Okay, so we talked about the burning velocity. Now, if I assume I have a flame front that propagates normal to this itself with the burning velocity, then I could also, you know, in 3 dimensions, I could try to understand the kinematics of such a flame with a field equation or with an equation. And so here we derive an equation that describes the dynamics of a front, a flame front that is, let's say, first of all, assumed infinitely thin because it is typically relatively thin, and the equation describes the dynamics of that flame. So earlier we said the position of the flame, the RDT, it changes by 2 aspects. One is just the surrounding velocity. So if no burning velocity and you have a flow velocity, that would just push this flame around, and so dRdt is equal to Vu. And then in addition to this, you have a burning velocity, so plus SL. And we can also write this in 3D. Then the xdt, the position or the change of the position of the flame, is a result of the local flow velocity plus SL times n, meaning this is the velocity, the burning velocity normal to the flame front. So this is indicated by these arrows. The flame always burns normal to itself. Okay, so from this then we can define or let's say now we define a so-called level set function. What's a level set function? The level set function is a function that's kind of defined in an arbitrary way, but it has the property that it's negative on the unburned side and it's positive on the burned side. And where that function g, we call it g, where that is 0, that's exactly where the flame front sits. Okay? So I said it's kind of defined in an arbitrary way. What the value is in the unburned, you know, how that is defined doesn't matter doesn't matter too much, let's say, as long as it's negative on that side and positive on the other side. Okay? Then I can derive an equation for this level set function. And if I have a dynamic equation, I can solve the equation. And at each time step, I can look at, you know, where is the function g equal to 0? What's the isosurface of g equal to 0? And that's exactly where the flame sits. Okay? So this says the flame sits at g equal to g naught. Of course, the value at which I define the flame is arbitrary. I could say the flame sits at g equal to 5. And then on one side is smaller than 5, on the other side is larger than 5. But we typically use 0 because it makes it easy. So g naught for our purpose is always equal to 0. Okay, so here smaller than 0, here larger than 0, at the flame front is exactly equal to 0. The flame normal vector then, we can define this from the gradient of g. So the gradient of g divided by the magnitude of the gradient, that gives you the normal vector normal to this isosurface. Okay, so then I can say, well, if the flame is always at the value g equal to 0, then I can say the substantial derivative of G. Substantial derivative means what is the change of what's the change of the value of G with time if I always sit on the flame? Okay, if I sit on the flame, then the change of the value of G is equal to 0 because it's always a constant. Okay, so I can say this is equal to 0. That's the condition for sitting on the flame. So the substantial derivative then is dg dt. If I write this in in an Eulerian or lab framework, plus dxf dt, dt times the gradient of G. And that has to be equal to 0. Okay, so that's the substantial derivative. So this is what's written here. So dx dt has to be evaluated at the flame front. Dx dt, we said earlier, is equal to v plus SL times n. So I can plug this in here, and you see, then I get dg dt plus, and then v dot del g, and then plus SL times n dot del g, and I put this on the other side, minus SL n dot del g. N was just defined or was evaluated as the gradient of G divided by this magnitude. So n dot del G is the magnitude squared divided by the magnitude, so just the magnitude remains. And so this is the equation I have. And you see, if I start out, I define this field G, and I know the burning velocity, then I can just solve this equation, and I can track the dynamics of the flame. The equation is a little complicated. It's a little different from what we usually have. It's not a conservation equation. There's no conservation property here. It's just a dynamic equation. We said we have a flame that moves with a certain speed, and that's it. Yes?
Is there a fundamental difference between this G equation and progress variable approach, where you basically define a normalized scalar between 0 and 1 using burn and under natural field mass fraction?
Yes, there is a big difference because so if I have a conserved scalar, if I have a progress variable, that's a species or temperature, and I derive that equation from a conservation equation that has conservation properties, whereas then it has a chemical source term and so on. Whereas this here has no conservation property. Actually, the value of this G in the unburned and the burned have no meaning. As a matter of fact, I was just going to say this. As a matter of fact, the equation was derived only for the flame surface. The equation doesn't even is not even well defined in this region and that region. So what you do is you define G in the unburned and the burned in a certain way. Typically, we say it's a distance function. Distance function means at G it's equal to 0, and the farther you go away, you always go along the normal distance. The farther you go away, the smaller the value gets or the larger the value gets. Okay, it's a distance function. Each point in space, the value of G tells you the distance, closest distance to the flame front. But that property is not conserved, so solving this equation, one has to do what's called a reinitialization every so and so often because the property is not conserved. But anyways, maybe that's even too much of a detail. This equation, it will tell you something about the dynamics of the flame, and later on we'll talk about premixed turbulent combustion, then we'll come back to this equation. What's interesting here is that if you have a front that looks like this, all nice, round, and smooth, and that front, it propagates always normal to itself, you see that this curvature here in this point will get larger, larger, larger until it's really a singularity, until you really get a kink. That's called here the Huygens principle, and that's exactly what happens. We see this also when we evaluate curvature probability density function in turbulent flames, for example, we see that there is a lot of, there's a large probability of finding small curvatures towards the unburned and very large curvatures towards the burned. Okay, so that's what happens. In reality, you wouldn't get a kink here because, as I said, the burning velocity, it depends on the curvature, and locally either it would be faster or the flame really opens at this point in a way. So from this, then one can say some things about a burner like this. This is a slot burner, and one can analyze this, but we'll skip over this, and you can look at this tonight if you have nothing else to do, let's say. Okay, so then let's look at the effect of stretch and curvature. I mentioned earlier that actually we should say strain and curvature. Actually, I mentioned earlier that curvature and also strain, local strain, have an effect on the flame speed. And so the stretch actually is defined as the change of the flame area, local change of flame area with time. So if you have an extensive strain, then this would make the flame surface larger. Or for example, curvature also changes the flame surface in time. And so both strain and curvature have an effect on stretch. Okay, so stretch includes both, and strain and curvature are the individual effects. So we can write the flame speed as an unstretched, so the local real burning velocity, we can write this as the unstretched burning velocity plus or minus a contribution here that comes from curvature, and then plus a second contribution that comes from stretch. Okay, so you see here, this is the velocity gradient tensor, which gives you times the normal vector to the flame, which tells you how the strain interacts with the flame. So these here, so this now is just it's called the Markstein number, and it's basically what this says. I can write this differently. So if SL, let's just look at the first one, is equal to SL0 minus SL0 times this L times the curvature. Okay, and I can look at a quantity like this. Let's say DSL divided by SL0 divided by the curvature. I want to make the curvature non-dimensional. What quantity would I use to make the curvature non-dimensional? The flame thickness. The flame thickness is the only length scale I have. Okay, so I would use so this is 1 by meter. So non-dimensional would be this times LF, and so I have an LF here also, or I put the also LF on the other side. So, or maybe I first write this like this. Maybe it's easier to understand. SL0 is equal to 1 minus, and then L divided by LF times kappa times LF. Okay, so and then if I evaluate this, then you see it just gives me L divided by LF. Okay, so this Markstein number is nothing else than basically the sensitivity of the burning velocity towards the curvature. Okay, it's just a coefficient that gives the effect of curvature on the burning velocity in a linear relationship. Okay, so that's how this is written. So curvature, we said the curvature is defined like this: is del dot normal vector. The normal vector we had that defined this as function of this level set function, and then I can write the curvature like this. Okay, so this is just a way how to evaluate the curvature using this level set function. And the Markstein length L is, well, here's of the same order of magnitude or proportional to the flame thickness. That's what we just said. That's the only length scale we have, so it must have something to do with this. And this ratio actually is called the Markstein number. What's interesting here is I just said the Markstein length, or the Markstein number then in this case, is nothing else than the sensitivity of the burning velocity towards curvature, okay? But in the same equation also, the Markstein length or the Markstein number is nothing else here than the sensitivity of the burning velocity towards strain, okay? So this equation here assumes that the sensitivity towards curvature and towards strain is exactly the same. That's not necessarily true. Apparently, it comes out of an analysis here, one-step chemistry, large activation energy analysis. But in general, you could think of these two coefficients here being different. Okay, and we'll see later on. We'll see an equation. We'll see an example how these are different. Okay, so this again is the expression we just had. Unstretched burning velocity, Markstein length here appears twice, and curvature and strain I can always locally evaluate if I know the flame shape. The Markstein number or the Markstein length can be determined from this relation here. This is a relation that comes from asymptotic theory, and it has two contributions here really. You see the first one here, this is the density ratio. The gamma here is the density ratio, and so you see this depends on the expansion. You know, how strong the heat release is, how much the expansion is. And the second one here, that you see that depends on the Lewis number, and if the Lewis numbers are equal to 1, the Lewis number, global Lewis number is equal to 1, then this whole thing here, the second term, would be 0, where the Lewis number is the ratio of the heat conduction or heat diffusivity, lambda over rho Cp, and the species diffusivity d. So you have these two different contributions, and this can be evaluated to get the Markstein number, and that gives then the effect here on these quantities. This relation here comes from two different groups here have evaluated these, Clavin and Williams, and also Matalon and Matkowski at about the same time. And Professor Matalon, he also sometimes teaches this combustion theory course here at the Princeton Summer School. So there's another quantity that appears here, is the Zeldovich number. The Zeldovich number is a non-dimensional activation energy. You see it's E divided by RTB, and then also it has a heat release parameter TB minus TU divided by TB. That's a non-dimensional heat release. Okay, so it combines these two values, and we'll see later on a different aspect where the Zeldovich number comes in, and we see the significance of this quantity. Okay, so this then here shows you some application to look at the effect of curvature. We'll not go through this, but this here is actually, this shows the actual effect of the curvature and the strain on the flame speed or the burning velocity by simulation and experiments. This here is an experiment that we did in our high pressure spray combustion vessel. I mentioned this earlier. We measure actually, what we measure really is SB, okay? The burning velocity with respect to the burnt gases, because the unburned velocity is 0. Sorry, the velocity in the burnt region in the spherical chamber, in the burnt region, the velocity is 0, which means the RDT is directly equal to the burning velocity with respect to the burnt gases, okay? So that's what we measure, and you see that's by a factor of the density ratio than SLU. Yeah, here, so the SLU is roughly 7 times slower. And then the lines here show you simulations, and actually these lines here also come from the asymptotic theory, different theories. One is just linear extrapolation, one is a nonlinear extrapolation, and you see both give you a value that's higher here and a value that's here the nonlinearity doesn't make much of a difference. Okay, and this here on the other side, that actually shows measurements in a counterflow burner. Let me just get some water. These are measurements counterflow burner, which were done by Professor Egorfopoulos at USC. So what they do is they have a counterflow burner. You have a nozzle on top, nozzle on the bottom. Both are pre-mixed. And then you have two pre-mixed flames, sitting in this burner, one burning towards the top, one burning towards the bottom. And then they change the velocities, which changes the strain. And then the burning velocity here, you see it changes. And then also there's an extrapolation that's done to zero strain. And you see here, these are simulations, the blue here, blue dots, these are simulations we did for the full two-dimensional setup. And you see here also that there's also nonlinearity here for very small strain. So these these are linear relationships. They hold for larger strain, larger curvature, but for very small strain, small curvature, you might depart a little bit from these linear relations, okay? These are simulations we did here together here with my former student, Guillaume Blancard, who's now professor at Caltech, one of my other students and one of Guillaume's students. And so here we did simulations of lean hydrogen flame and lean propane flame. Hydrogen has a Lewis number smaller than 1. Propane has a Lewis number larger than 1. And then these are the spherical flames I showed you. So this here would be, or maybe we start here. Lean propane flame, Lewis number larger than 1 is similar to methane, let's say, and we get the same behavior as this. Okay, smaller, if we go to zero curvature, then the burning velocity goes up. That's the same you see here. You go to zero curvature, then the burning velocity goes up. Now in a simulation also we can do the opposite. We can ignite on the outside and then have the flame, a spherical flame, burn inwards, okay, until everything is burnt. And then you see then the dependence here is exactly the opposite. Then the larger curvature gives you higher burning velocity. And then for hydrogen, which has a Lewis number smaller than 1, you see it's exactly the opposite. Here we go outward, inward, and here we go outward, inward. So for hydrogen flames, exactly the opposite. Shows you the strong effect of the Lewis number. Okay. So then we can also look at the this thermodiffusive instability, which is also an effect of Lewis number. And here I just want to show you what causes these instabilities. We have these two instabilities. One is the thermodiffusive instability, one is the hydrodynamic instability. The thermodiffusive instability is caused by non-zero, non-unity Lewis numbers. The hydrodynamic instability is caused by the heat release itself, and so that is always present no matter what. the thermodiffusive instability is only present if the Lewis numbers are just right. So we can look at a flame that maybe, so let's say you have a flat flame. Here's the unburnt, here's the burnt, and so this flame burns here from top to bottom, okay? Now we can perturb the flame. So I put a perturbation here, maybe this sine-like function, and then here I have positive curvature, here I have negative curvature, okay? So if I look at this relation, positive curvature means the burning velocity is a little slower, negative curvature means the burning velocity is a little larger, okay? If the Mach-Speed number is positive, okay? Now, turns out for lean hydrogen mixtures, the Mach-Speed number actually is negative. And if you look then at the dynamics, let's first look again at positive Mach-Speed number. We said this is my perturbation, positive curvature, positive Mach-Speed number. I have a minus sign here, means the burning velocity here is a little slower than in other places. So it will go back to the undisturbed case, okay? So that effect actually, it takes out the perturbations. But if the Mach-Speed number is negative, which it is for lean hydrogen flames, then here I have positive curvature. Positive curvature means now I have minus sign, and L is negative, meaning this is positive. So the burning velocity for positive curvature will be a little larger than the unstretched burning velocity, which means this point will burn faster. Here it's the opposite. This point will burn more slowly, and you go from the initially perturbed state to this dotted line, which means now you make the curvature even larger, which means this thing will burn in these points even faster, and you see you have an instability, okay? So that's the mechanism. This is how this looks like. This is simulations also were done in the same paper. And you see initially this is undisturbed, and you get these patterns. This here is actually a very small cell. In reality, this cell is actually too small. These are simulations. These are large simulations that we did recently, one of my PhD students. And this is a very large cell. And then you see these patterns, very characteristic patterns here appearing. And this is a paper here actually that will be presented at the Combustion Symposium in Dublin. And you see how this initially starts out, and then you get these fingers here which burn and they move sideways, and then they touch each other. This is temperature, and you see that I said this earlier, for these cases where you have strong curvature towards the burnt, actually the flame opens, it extinguishes in a way, and you get these very low temperature regions here in the burnt gases. This is from experiments here from this paper, and you see that the structures we see in the simulation here are very similar to what we see in the experiment. Okay, so what's interesting also is that these structures, they grow, but then at some point they don't grow any further. They just keep a certain size, and that's what was shown in this paper. This just shows, we'll talk about turbulent combustion later on, but this shows that also for turbulent combustion, this has a big effect. This shows the burning rate here of a lean hydrogen air mixture at a certain equivalence ratio, and this is a turbulent flame, okay? And you see the turbulent flame has some thickness, burning rate is temperature, and if we go to even leaner conditions, then you see the flame all of a sudden becomes very, very thick. And so the only difference here is this 0.4, this 0.31, and this is caused by the instabilities that you get at that point. So let's see, we have time to quickly, yes, we have a few more minutes. So let's look at the hydrodynamic instability also. The hydrodynamic instability I mentioned just comes from the heat release. Turns out that if you have a flat flame and you have a streamline coming in here, then that streamline will just hit the flame, and at the flame you have combustion, heat release, density goes down, the flow will be accelerated and the velocity will be much faster here in the burnt gas, okay? But now if we have a small perturbation, look at this again, we have a small perturbation, then the streamline approaches here the flame, and when it approaches the flame, or when it goes through the flame, you will have acceleration, and because of this, you will the streamline will divert, and so because of the pressure effect, actually it diverts a little bit even before the flame. So you have a stream tube here that comes towards, so this is a tube of constant mass flux everywhere that approaches the flame, and you see the streamlines are diverted a little bit, which means if the area here gets larger of this stream tube, then the velocity here locally becomes slower, which means now if the velocity locally here is a little lower, then the flame can propagate in this direction, okay? Here, on the other hand, the velocity is a little higher, so it pushes the flame a little bit in this direction. And you see that an initial small perturbation, then because of the effect of heat release here, will become larger with time, okay? So that's the effect that you see here. And again, that's an effect, that's just explained here with a lot of words. But that's an effect that has nothing to do with the Lewis numbers. It just comes from the fact that you have heat release. So that is an intrinsic instability that is always present because every single flame always has heat release. So why don't we see this all the time? Why don't we see flames becoming unstable immediately all the time if this hydrodynamic instability is always there? This is called, also called the Darrius-Landau instability. Say again? Pardon? Sorry, I didn't. You don't have a mic. No, it's okay. You don't have a microphone. I assume you said the right thing. So let me repeat it then. If you had no stabilizing effect, this is an instability. It will always be unstable. But there's a stabilizing effect. What is the stabilizing effect? We saw earlier that the thermodiffusive instability. It's an instability if the Mach-T number is smaller than 0, but if the Mach-T number is larger than 0, that was actually a stabilizing effect, okay? And so if we do then a linear stability analysis, keeping both of these effects, the Lewis number effects and the hydrodynamic instability or the heat release, then we get a so-called dispersion relation here. The sigma, this is sigma as function here of k, which is the wave number. So what this means is I have initial perturbation at a certain wave number, and this tells me the growth rate for a given wave number. Okay, growth rate is different for different wave numbers, and that's what this is. So it's the relative growth as function of time of an instability, of an amplitude of an instability for a given wave number. And if the Mach-T number is 0, meaning there's no diffusive effect, then this is the dispersion relation, which means the growth rate. So what this means, growth rate positive means it's an instability, negative means is stable. Okay, growth rate is negative means perturbations always go away. So for Mach-T number equal to 0, so if we only look at hydrodynamic effects, then this is always positive. So the flame is said to be unconditionally unstable. Okay, there's no condition under which it's stable. But if the Mach-T number is positive, the larger it is, the different is the shape here. So this here, for example, is the dispersion relation for a given Mach-T number. So you see it first goes up. First, for a very small wave number, the Mach-T number doesn't have an effect. For larger Mach-T number, then it becomes more stabilizing, and then there's a critical wave number here above which the instability does not occur anymore, okay? So, and the larger this Markstein number is, the large, so this here is large Markstein number. The larger the Markstein number is, the smaller the unstable regime here actually is, okay? So what's interesting about this is all linear stability analysis, but what's interesting, it really shows you exactly all the quantities on which this depends. Depends here on R, here is the density ratio, L here is the Markstein number, and so on. So it gives you then a condition. If we look for sigma equal to 0, then it gives you a condition here also for this critical, wave number above which the instability does not occur anymore. Okay, so this is what this says. And then here there is the analysis. If you're interested in how to do the linear stability analysis, this goes now through a lot of equations here. This is why we skipped this. It's too much. But you could actually look at this. So this brings us then to the end of this. And then now in the next lecture, we'll continue talking more about premixed flames. But now we'll have a break for 15 minutes.